Welcome back. This is continuation of lecture on thermohaline circulation. This is part of NRC in marine science. This lecture is on thermohaline circulation, part number 4. In the 3 parts, we have briefly looked at the thermohaline circulation, its components, how the water flows from one basin to the other, and how it returns. We also looked at conditions required for a water parcel to sink into the deep ocean. There are 2 conditions that are to be satisfied. One of them is that there should be sufficient loss of buoyancy, and the next is that the water column should be sufficiently weakly stratified. Once these conditions are met, the water parcel sinks and flows. We also have seen some slides which shows the amount of water that is involved in different components of thermohaline circulation. In this 4th part, I would like to give you a brief idea of a simple dynamical model that is used for explaining the thermohaline circulation. What should the simplest of models of thermohaline circulation should try to explain? That is what's shown in the schematic of the thermohaline circulation. The processes involved are the sinking in high latitudes, which goes all the way to the deep ocean, and then the spreading of that water masses, its slow upwelling that is happening in the interior, and the return flow. This is what the simple models should try to explain. Now, in the interior of the ocean, below the wind driven layer, it can be assumed that the flow is largely geostrophic. So, in the geostrophic flow, the horizontal pressure gradients are balanced by the Coriolis force. The Coriolis force is written as Fu and Fv. Fu is the meridional component of Coriolis force and Fv is its zonal component. So, here these equations represent the geostrophic balance. The first one is the zonal momentum equation, which simplifies in terms of geostrophic flow into Fv equals 1 by rho naught del P by del x, and the meridional equation is Fu equals minus 1 by rho naught del P by del y. Del P by del x and del P by del y are the zonal and meridional pressure gradients respectively. Fu and Fv are the components of Coriolis force. The third equation is the equation of continuity, which states that del u by del x plus del v by del y plus del w by del z is equal to 0. It is possible to eliminate pressure gradient from the first 2 equations. What need to be done is to differentiate the first equation with respect to y and the second equation with respect to x and add the 2 resulting equations. Then use the continuity equations. When we differentiate the first 2 equations and add them, you can get the first 2 terms of the continuity equation. If you substitute what you get after the differentiation and summation into the continuity equation, then you will get this equation, which states that beta v is equal to f del w by del z. Here beta is the variation of Coriolis parameter with latitude, beta equals del f by del y, which is equal to 2 omega cos phi by r, where phi is the latitude and r is the radius of the depth. F equals 2 omega sin phi. Omega is the angular velocity of the rotation of the earth and phi again is the latitude. U, V, W are the 3 components of velocity. U is the zonal component, V is the meridional component, and W is the vertical component. Del W by del Z gives you the vertical variation of horizontal velocity. Now, integrate this equation from the ocean floor to a mid depth. The mid depth is roughly where the upwelling happens to complete the thermohaline circulation. So that's integral here, VdZ, integral from the bottom of the ocean to the mid depth level. Then assume that the vertical velocity is 0 at the bottom of the ocean, which means that the water cannot penetrate the ocean floor. So if you apply that condition, then on the right hand side you said F by beta into W at mid depth, vertical velocity at mid depth. And we know from whatever we have seen in the previous parts that the vertical velocity is upward, the upwelling is upward, and which means that F by beta W mid depth should be greater than 0. Now this demands that if the vertical velocity in the deep ocean is upward, there should be a corresponding movement of water towards the pole to be in dynamical balance of vorticity. Therefore, this demands that there should be flow in the interior of the ocean that is directed towards the poles. Now, if the flow in the interior of the ocean is towards the poles, there has to be a flow which compensates, and that compensating flow should be southward. Also, that compensating flow should be done by an western boundary current. Therefore, this simple dynamical model, which assumes that the flow in the deep ocean is geostrophic, and also which assumes that there is no vertical velocity at the bottom of the ocean. If the upwelling associated this flow is upward, there should be an interior flow of the ocean towards poles, and in order to compensate that poleward flow, there should be a deep western boundary current. This theory was proposed by Henry Stommel in 1958, and this figure shows you a figure from his paper, which is a classic paper, and this figure shows you the streamlines of flow. The flow in the interior is northward, and in order to compensate that, there is a western boundary current deep into the ocean. Flow in the deep interior of the ocean is poleward, and return flow is equatorward along the western boundary. And this is the classical picture of abyssal circulation as described by Stommel using purely theoretical conditions. Later observations have indeed demonstrated that there does exist deep western boundary current in the ocean. Now, the last topic of this lecture is on the impact of global warming on thermohaline circulation. Thermohaline circulation is important also for the heat budget of the oceans. The oceans receive a lot of heat in the tropical region, and the heat, the excess heat that is received in the tropic has to be transferred to higher latitudes. The process is done by approximately equal proportions by atmosphere and oceans. And this is a picture which demonstrates this fact. These are all zonally integrated quantities, and what is plotted here is a transport of heat in petawatts, PW, that's 10 to the power 15 watts. The positive values indicate northward transport and negative values indicate southward transport. There are three curves here. There are three colors here. One is black, which shows total heat transport. The red curve shows the heat transport by the atmosphere, and the blue curve shows the heat transport by the oceans. There is large amount of heat transport happening by the ocean circulation in both hemispheres. There is transport of heat towards higher latitudes. The different curve shows the heat transport deduced from different data sets. So the solid lines shows the heat transport deduced from velocity potentials, and The dashed line shows the heat transport deduced from heat flux, and dotted lines shows from observations. All three curves shows consistency among various data sets in the fact that there is roughly equal transport of heat from the lower latitude towards the pole by both atmosphere and oceans. What happens to the thermohaline circulation in this global warming regime? It's well known that there is warming of the oceans, and this warming is attributed to anthropogenic impacts. Owing to the warming, there is an increase of sea surface temperature. When the sea surface temperature is higher than it was before, there is more melting of ice. More melting of ice means that there is more addition of fresh water into the ocean. If there is more fresh water added to the ocean, there is dilution of seawater and the density of the water parcels decreases. As a consequence of decrease in density, the sinking and deep convection that is happening in the high latitudes will decrease. This suggests that there will be a weakening of the strength of the meridional ocean circulation. There is less volume of water sinking, and the amount of sinking to a large extent dictates the strength of the meridional ocean circulation. Thus, the warming of the ocean would lead to more melting of ice, and consequently there will be a weakening of the meridional ocean circulation. If the meridional ocean circulation is weaker, then that would lead to a slowdown of ocean meridional heat distribution. The transport of heat from the lower latitude to the higher latitude would decrease. If there is a weakening of the meridional heat transport distribution, there can be accumulation of heat in certain regions and reduction or deficit of heat in certain other locations, which means that the distribution of sea surface temperature in the global oceans would change. Now, the atmospheric processes are controlled to a large extent by the changes in sea surface temperature. If the sea surface temperature increases, there is a possibility of larger rainfall in those regions. So, changes in global sea surface temperature anomalies can lead to changes in large scale anomalies in rainfall, and this can also lead to extreme events. Now, there have been model studies to document these processes. Let me show you one example. This experiment was done by Shang and Delworth, and this was done by using a coupled ocean atmospheric model. In order to understand a possible impact of global warming on the thermohaline circulation, what Shang and Delworth did was to carry out two experiments. In one experiment, the model was run using present day conditions. In another experiment, they wished to isolate the impact of increased freshwater supply into the northern Atlantic. In order to achieve this, what they have done is to add an extra amount of fresh water into the North Atlantic in the region between 55 to 75 degrees north and 63 degrees west to 4 degrees east. And this addition of extra fresh water was done for a period of roughly 60 years. And this figure kind of summarizes the result that they have obtained. So there are two curves here. Both of them shows the strength of the thermohaline circulation in Swerdrup. One Swerdrup is 10 to the power of 6 meter cube per second. The scale on the vertical axis shows you the values in Swerdrup. The black curve shows the strength of the Atlantic thermohaline circulation in the control run. The red curve shows the strength of the thermohaline circulation in the perturbed run, where they had added an additional amount of fresh water into the northern Atlantic. It's very clear that The strength of the thermohaline circulation decreased when an additional amount of fresh water was added into the model. The strength of the thermohaline circulation was roughly 15 centigrades in the control run, but it decreased steadily with the addition of the fresh water and settled down to a value which is less than 5 centigrades when the excess fresh water was present in the model. The summary is that addition of large quantity of fresh water in the North Atlantic results in a weakening of the Atlantic meridional ocean circulation. How does this weakening of the thermohaline circulation affect the climate patterns of the world? That's summarized in these two figures. The top panel shows you the anomalies of sea surface temperature, and the bottom panel shows anomalies of rainfall and sea level pressure, which is a response to slowdown of AMOC. So, when the meridional ocean circulation is weaker, the SST pattern shows more warming in the southern Atlantic, and also patterns like El Nino in the tropical Pacific. During an El Nino, the sea surface temperature tends to be warmer on the eastern Pacific and cooler on the western Pacific. And these anomaly patterns have its implication to the atmosphere, though there is a decrease of monsoon rainfall over India and also the tropical rainfall in the Atlantic and Pacific Oceans. The intertropical convergence zone, which is located slightly to the north of equator in a normal climate, tends to shift toward when the meridional ocean circulation is weaker. In brief, the slowing down of thermohaline circulation can have impacts on a global scale. With that, I would like to end this chapter on thermohaline circulation. Here is a list of references that has been used in this talk. The one by Marshall and Plumb and by Tiley et al. Are nice books on oceanography. They have given excellent chapters on thermohaline circulation as well. The paper by Marshall and Scott has explained in detail the process of deep convection in the ocean. The abyssal circulation is a classical paper by Stommel in 1958. The papers by Trenberth et al. And Shang and Delworth gives you impact of climate change on global thermohaline circulation. Thank you.